Everything we've built so far lives on a line. A bar, a rod, one dimension. And that was the right place to learn. But the real world isn't a line. Real parts look like this: a plate with a hole, an L bracket, a gear tooth. There's no single formula for these, and no way to stretch them onto a line. We need genuine two-dimensional finite elements. Here's the reassuring part. The method itself doesn't change. Element matrices, assembly, boundary conditions, solving KU equals F, all exactly as before. What's new is just three things: the elements become triangles, the shape functions become two-dimensional, and we need a little more bookkeeping to track which node is which. That's the whole leap. Let's start by chopping your real shape into triangles. Start with a solid 2D region, here, a simple plate. In one dimension we split a line into segments. In two dimensions, we tile the area with triangles. Lay down a few nodes, connect them into triangles, and the plate becomes a mesh. This is the two-dimensional version of discretization. The triangles are our elements, the corners are our nodes. And just like in one dimension, a finer mesh means more accuracy. Add more triangles, and the model resolves the solution more sharply. The same convergence idea, now spread across an area. The mesh is the model. Now we just need to understand one triangle, how a single triangular element behaves, and then assemble them exactly like before. The simplest 2D element is a triangle with three nodes, the constant strain triangle. In episode 2, each 1D node had a tent function. Here, each of the three corners gets 1, 2, but now it's a surface. Watch the shape function for node 1. It rises to a height of 1 right at its own corner, and slopes down to 0 at the other two. A tent stretched over the triangle. Nodes 2 and 3 have their own tents, same shape, different peak. Three planes, each owning one corner. And just like in one dimension, the three tents add up to exactly 1 at every point inside the triangle. Partition of unity again, the same principle, one dimension higher. So any quantity inside the triangle, temperature, displacement, is just a flat plane through the three nodal values. Linear, simple, and exact for any straight variation. That's why it's called the constant strain triangle. In one dimension, assembly was easy because the connections were obvious. Element 1 touched nodes 1 and 2, element 2 touched 2 and 3, and so on, in order. In two dimensions it's not so tidy. Here's a tiny mesh, 4 global nodes, numbered 0 to 3, split into two triangles. Each triangle grabs 3 of those nodes, but not in any neat order. So we keep a connectivity table for each element, which global nodes are its local corners 1, 2, and 3. Triangle A uses nodes 0, 1, 3. Triangle B uses 0, 3, 2. And that's all the table is for. It tells the assembly step exactly where each triangle's 3x3 matrix gets added into the global system. The shared node 0, used by both triangles, is where their contributions overlap and add, just like the 1D case. Notice we didn't solve anything this episode on purpose. We earned the geometry first. And now we have all three new pieces: a triangular mesh, the two-dimensional shape functions, and the connectivity table that drives assembly. And everything else we need: assembling the global matrix, applying boundary conditions, solving the system we already built back in phase 1. It carries over unchanged. So next episode, we put every piece together and solve our first genuine two-dimensional problem, watching a temperature field spread across a real plate, computed entirely by code we wrote ourselves. This is where it finally looks like the software you've seen, except you'll know exactly what's underneath.